Now we have used the for loop and we see all our Gini scores down here, right? This is the vector that holds all our values. We have all our Gini scores. Now we need to find the Gini score that is the smallest. The Gini score that's the smallest, that will tell us which value we should use for the splitting function. At least when it comes to choosing a splitting function, a splitting value in the sepal.length column. Easy way to do this is create a table. So I will create a table called SLDF, sepal length data frame. You should use data table, whatever. And I'm going to put the Gini scores in here. So I'll call it, first I'll put the actual values that I used, which was sl.array, and we'll call those, I can call it val equals sl.array. And for the Gini, I will put in the Gini scores. I run this. Oh, a little problem here. Is there a problem? Just make sure the length is the same. 24 sl.arrays and okay. So I don't know why we got the warning. Let me run SLDF again. Maybe I need to run my library.table command. Just in case. Alright, let's try that again. Okay, good, we're good. So now we have the table SLDF table, right? If I were to run this. Right, I have the values and Ginis. I need the smallest Gini. I need the row that gives me the smallest Gini. How do I do that? I showed you guys that before. We're just going to filter for it. How do we filter for it? We use the function which.min again. And remember, which.min gives you the row number of the smallest value. So here I'm going to give it the column Gini. So which.min will look at all the values in Gini, will find the smallest value, and then give us the row number of the smallest value. I go to execute this. Bam. It turned out when it came to sepal.length, that our value that we split on should be 5.5. That gave us the smallest Gini score. Excellent. All right, so I did sepal.length. Now I just have sepal.width, petal.length, and petal.width as well to go through. I have to go through each column and then compare the final values. So what I'm going to do here now is I'm simply going to copy and paste. Again, we could have probably wrote a function and do this, but we can also copy and paste, come down here. I will say this is for sepal.width. Bam, all right. So here again, we just need to figure out what values we're going to go through again. And I think I do that for you right here, sepal.width. I do table. Yeah, let's go ahead and do that. So we're all on the same page. I'll go to my data train, my sepal width column, see all the unique values. And again, we'll just check it out right here. Okay. At this point, there'll be 2 values. At this point, there will be 4 values. At this point, there would be 2 plus 2. 2 plus 2, that's 6 values. It still doesn't make the cut. So I come to here, and less than 2.6 would finally give me, 2 plus 2 is 4, 6, would finally give me 7 plus 2 is 9, yes. So at this point, I need to shoot for sepal.width, I need to start at 2.6. Because at 2.5, less than 2.5 would give me just 6 items, 6 rows, which obviously violates the min bucket rule, the min bucket condition. So I'm going to start at 2.6. So I'll come here, and I will create a, let me copy and paste some of the, Do I have, if I have it down here? Where is it? That's all right. I just want to copy. All right, that's fine. I don't have it. I'll just do it here. Right, and we're going to call this sw.array. Now it's going to equal, get the second copy actually. Right here. That's what I wanted. All right, this is now going to be sepal with.array. Sepal with. And now this is going to be greater than or equal to, what do we say? It's going to start at 2.6. All right. And it's going to go to, let's go all the way down here. Not this, this is 3. 3.8 gives me 7, so to 3.8. All right, I'm going to get the unique, here we go, sepal with values. I'm going to sort it. Down here, you can confirm that we just got 2.6 to 3.8 values. See that? Boom. And we're ready to go. Let's make a few more changes here. Change this for loop right there. And again, we're going to change these values to sepal with. And I believe everything else stays the same. All right. So obviously this is going to change right here. It's going to be sepal with, and this is now sepal with array, SW array. And I think everything's ready to go. So let's go ahead and give it a go. Oh, sorry, that should be W. Let's give it a go. Bam. And now for my sepal width, I have my value 3.3 with the smallest Gini score. All right, 3.3, 4.443263. All right, I should be saving all these. I'll just run them all. I'll just run this line 90 and the other lines together when we finally have it all. All right, so that's sepal width. Now we have to do petal length. And again, I'm going to just copy this. Make the changes I need. This is now going to be petal length. All right, petal length. Let's go ahead and make that change there, make that change there, make that change there. Instead of SW array, this is going to now be PL.array. PL.array. All right, before we move any further, let's change the numbers before we forget. All right, so I come here. At this point, no. At this point, this would be, at 1.4, this would be 5 values. At 1.5, bam. I have to start at 1.5. All right, and I'm going to go all the way up to, this would be 1 plus 2 is 3. That is 1 plus 2, 4, 5, I think 6.1, 3 plus 1 is 4, 5, 6, 8, okay, so 6.1. So we are going from 1.5 to 6.1. I made my changes in the lines 95 and 96. Let's see where else I need to make a change. Yes. I need to make a change here, here. This is good, this is good, this is good, this is good. That's all good, that's all good. Yep, now this is going to be petal length, PLDF, PLDF, and this will be PL for petal length dot array. Okay, and now we're ready to rock. And do this one. Ooh, Val 4.8, Gini 4.36753132. For those of you guys paying attention, that should be familiar. That value and that Gini score should be familiar to you. But let's move on finally to petal width, which is our last column, which is also a numerical column. This now becomes width. This is width, that is width, that is width, and that is width. Width, width. This becomes PW. And that becomes PW. So let's see what we're dealing with width. Okay, cool. All right. I can't take 0.1. I gotta take 0.2. I can't take 0.2 actually, because less than 0.2 is just 3. I gotta go to 0.3. So this is gonna be 0.3. All right. And I'm gonna go up to, this is 6. This would be a valid value, so I'm gonna go up to 2.3. All right. This is good, this is good. I changed that. I changed petal width, petal width. Good, good. Good, 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 good. Right, right, come here. Petal width, and this is PW array. So I go ahead and run this now. See, once you write the code, you gotta make a few changes and you're good to go. And I got my value, 1.8. All right, time. I now have calculated the optimal Gini scores, or the optimal splitting value for each column, and got the Gini score, the smallest Gini score. Obviously, that's what the optimal value is. It has a small Gini score. Let us compare our values now. Okay, let us compare our values. So I have let's do, just make it easy on ourselves. We can do I'm thinking what's the easiest way to do this. I can just run it. All right, so this is petal width, petal length, sepal width, sepal length. Let us all compare it now, guys. All right, there we go. Side by side. Which is the smallest Gini, guys? Hey, why sepal length and sepal? Look how sepal length and sepal width have the same Gini. Suspicious. Nevertheless, if I go down to my PLDF right here, guys, petal length, that is the smallest Gini score. I will be taking the value 4.8. So what this comes down to, guys, is basically we compared all the columns, all the values, and the one value that gives us the smallest splitting function, the smallest Gini score, turns out to be petal length. So when we do this, this is why we end up getting, right? And again, we're going to split it by the value 4.8, petal length less than equal, greater than equal 4.8. And of course, we end up getting, if I scroll away here, we end up getting our first split right here. We end up getting our first split right here, right? Which is familiar to you guys because, scroll down, all right? Which is familiar to you guys because that is exactly what happens here, right? From here, that's what RPART did. It split, and here I have the results here. So somewhere along the lines, it looks like I made a mistake because I do have different Gini impurity scores for sepal.width and sepal.length. Let's see. It's probably sepal.width. Let me go back real quick. That's bothering me. All right, let's do width, width, width. This will be an array, sepal width, boom, 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 boom. Let's run this again. Okay, now I got the same value. I think I might have changed something. All right, so now I have the same value. Okay, now I got the correct value. It doesn't matter. Either way, it's still going to be petal length. And you'll see on the first split here, RPART, what do they do? Petal length less than 4.8, petal length, yes, petal length greater than or equal to 4.8. Or no, what happened? And so it created this box right here, boom, which ended up being a terminal node when it kept going. And it created this box right here, boom. And that's the RPART algorithm right there. We did our first split. Now we want to do our further. We want to go further with our splits. We go to each box now. We have to do the same thing we just did for the main box. We have to go ahead and do it for this one. Then we have to go for this one. When we split this one and we split this one, we're now going to compare not just these, not just the 4 values among here. We're gonna also compare the 4 values among there, right? So you can see how this gets more complex as we go. Now, the other step we have to do, we're not done. We have to test the complexity parameter, the post-pruning parameter, All right, we have to test this out. Now, how do we test this out? When we split, all right, we got our result. We split the data sets. We're going to split the data sets, right? We're going to have one table. That's going to be all the values where it's less than 4, petal length is less than 4.8. We have another table that's going to be all the values where petal length is greater than or equal to 4.8. Okay, what we're going to have to do now is we're going to have to create a confusion matrix from the split. How do we do this? It's quite easy, all right? So we start off with, we can start off with either box, it's fine. I'll go ahead and start with the left side. And the left side, right? And by the way, notice we're doing a group by here, because if we go back to my R table, right? Petal length, let me go ahead and do right here. Right, if you saw the table, just to prove it to you. All right, show what I'm talking about. I'm gonna call it left table equals data train petal dot length less than 4.8. Right, so this is left table. You get a whole table of values, right? You get a whole table of values, right? All those values are there. It's just that all the values there are where petal length is less than 4.8. Wherever petal length here in this each row was less than 4.8, this moved to the left dot table. In the right table, what happened is we got all the rows where petal length is, you guessed it, greater than or equal to 4.8. All right. Same concept. Now what we need to do, just like before, we need to count up how many species there are on the left table. We need to count up how many species there are on the right table. So again, I can just simply do, I can use the group by method. I can use the table command. Either or is fine. Right? Let me do the group by, just so you guys get better with it. So I want to basically see. For all the rows, I want to see basically the count. For all the rows, I want to basically see the. If I just ran this part, it just literally gives you the rows, all the rows of left dot table, right? But if I say by equals species, now it's going to give me the count of each row according to each species, which is what we have there, 2733, right? And that ties into. This is what we see. So that's what the 2733 is. It's literally how many instances of 20 setosas there were in that table, how many instances of 30 of versicolors. So that's what you're seeing here. It's literally the count of each species. Given that, now how do we create a confusion matrix? Again, start with the left node. See the species that has the most count, the majority. That would be versicolor at 33. Done. So what I first want to do is, actually let me go ahead, show you how I do this. I mean, you can see how I do it, but I mean, if you want to walk through it, right? walk through it. Fine. All right. So I go ahead and I first set up my, I'll do an alphabetical order. I'll set up my my confusion matrix. So I do, what is it? Setosa, Virginica, and versicolor, right? Is that the order? Oh, sorry. Virginica, I don't know how to spell. That's actually I. Alrighty. And now you just take this, put it down. Boom. All right. So we set this up. Now what's happening? Okay. So find the majority in this child. The majority is versicolor. Excellent. That means this is the majority. I'm starting with the versicolor row. That's the majority. And now I'm just going to lay out in each column, right? Because this is now considered the versicolor child. So if it's a versicolor child, I'm looking at the versicolor row. The child, whatever the majority is, that becomes that node. So this node is the versicolor node because that's the majority. If it's the versicolor node, that means that node pertains to these rows. So now, because that's the versicolor node, I go to the versicolor row. So I'm at the versicolor row. Now, on the versicolor row, I put the count of each one of these values. All right? Setosa is 27. All right? Versicolor, 33. Virginica, 0. See, that's how it goes. That's how you place it, guys. All right, now I go to the next child. This child, the highest number of species goes to Virginica. Therefore, this is a Virginica child, right? This is a Virginica child. So now I'm going to go to the Virginica row right here. And now I'm going to start placing the values. Setosa is 0. Versicolor is 5. Virginica is 40. All right? I have no more children. Therefore, Setosa, nothing there. It just all becomes 0. Right? If there was a Setosa node, I would use it. Because there's not, it just goes to 0. All right? From here, we have to now calculate the accuracy. We want to get the, remember, we're now calculating the complexity. We're now calculating the cost of complexity, and we have to make sure that our cost of complexity for this split is less than or equal to, actually greater than or equal to whatever our complexity parameter is, which by default is 0.01. All right. How do we calculate the cost of complexity? All right. First, we need our error term. What's our error term? It's 1 minus accuracy. What the hell is accuracy? Yes. Accuracy is the diagonals. Let me get a little fancy here. The diagonals okay. Right? Add up the summation of the diagonals, because those are all the ones predicted correctly, divided by the total number of the whole confusion matrix. So on my numerator will be 73. My denominator will be the summation of all these values, which ends up becoming, let's add it up. Let's sum it up all here. It comes out to 105, obviously. All right? So what is 73 divided by 105, guys? .6, whatever. That is my accuracy. Now I need my error term, or my error rate, which is simply 1 minus my accuracy. Oops. 1 minus. Bam. There's my error rate. Now, okay, I got my error rate. Now what's next? Now I need to get my relative error. How do I get my relative error? I get my relative error by dividing by my root error or my baseline error. Okay? By my root error or my baseline error. What is my root or baseline error? Your root or baseline error for all the calculations is your initial node, the error of your initial node. The error of your initial node. What is the error of my initial node? If I go to data train and I simply do table, right, of my training data, oops, sorry, data train, $species, that's what I wanted, boom, okay, I have 27 Setosas, 38 versicolors, 40 Virginicas. Which one do I have the most instance of? Yes, Virginica. Therefore, the root node, which is the data train, is considered a Virginica root node. If it's a Virginica root node, how many of the other classes are mislabeled or quote-unquote should not be there? In other words, what are the ones that are not Virginica? That's Setosa and versicolor, 27 plus 38, which gives you, yes, 65. So there's 65 that are wrong out of 105 values. Ladies and gentlemen, that is your root error or your baseline error, right? And every time you calculate your error rate, and for after every split, you're going to divide it by your root or baseline error, which is this. So I take this, place that, let me actually just do the math right here. 65 divided by 105, boom. And this is now my root error, baseline error. All right, guys, boom. To get my relative error now, my relative error, and you guys saw this in the CP table, that will now be whatever my error rate is over the split divided by my root error or base error, and now I have my relative error. Okay? I have my relative error. Now, I'm supposed to divide this relative error by the new split or splits. In this case, we just had one split. We just had one split. So this divided by 1 is going to give me whatever that value is. This value is clearly greater than 0.01. Therefore, we do not prune the split. This split stays. It's good. It does not violate our complexity parameter. Our complexity parameter. And so this split is good. This is why it's a post-pruning. It's a post-pruning setting. Because whereas the other three, we take those into account before we make a split, this one we take into account after we do the split, and we might reverse the split. RPART will reverse the split or prune it if it gets violated. That's why it's considered a post-pruning parameter. That's why the difference between pre-pruning, post-pruning. All right, and we talked about before how we like to set the CP to 0 and just lax the pre-pruning parameters just so that we can have a deep tree and find the optimal complexity parameter to work with for our model. All right, so boom, we're good. We're ready for the next splits, which I leave to you guys to do. All right, it's a good practice for you guys. I leave for you guys to do. Knock yourselves out. All right, and at this point, we're good. We're done and finally done with the video. And we're now done with part F, and hopefully, I hope you get a good understanding and feel now for how RPART works. Now, it's clear to see, now that we've run through RPART, that when you have massive amount of rows of data and columns, your amount of calculations goes up when you're doing RPART, right? If you have massive amount of data, the algorithm is going to take a long amount of time, right? Which is why there's other algorithms out there that we will also touch upon, all right? We're going to go over no matter what, right? The cooler stuff. I love RPART, but obviously there's cooler stuff out there. But now you have a fundamental understanding of how RPART works, and I encourage you guys to go take it to the next level, finish off the analysis, and finish your tree, just like RPART did. All right, guys, so this concludes our video, our part 2 of the video. And I'll see you guys at the next video or the next class. All right, have a good day. Bye-bye.